Okay, so last time we looked at graph theory and linear algebra and the notion of independence, and then towards the end I talked a little bit about Gaussian elimination, and today I am going to talk about linear programming. It's one of the most widely applied uh, techniques from linear algebra, and it appears everywhere in practical life. So, let me take an example from earlier lectures where we were talking about separation of points. So, separation of points, if you recall what the problem is, you have two kinds of points, maybe some blue points and some red points, and what you want to do is to draw a line that separates them, right. You want to find a line that separates the blue points from the red points, and here is a line, all the red points are on one side of this line and all the blue points on the other. And so, in the future when you have a new point, you can try to classify it as to whether it should be a blue point or a red point. In practice, the blue points might be pictures of dogs and the red points might be pictures of cats, and you want to decide when you get a new picture, is it a dog or a cat. Okay. So, that is a somewhat fanciful example, but you can imagine much more practical examples. So, so basically you have to make a decision problem based on the geometrical sort of nature of the data points. So, let us just say that these data points are, there are n of them, we have x 1, x 1, okay, we have x 1, y 1. So, the points are x 1, y 1, damn it, x 1, y 1, x 2, y 2, x k, y k, and let us say these are the blue points, and then we have red points which are x k plus 1, y k plus 1, x k plus 2, y k plus 2, x k plus 1, y k plus 1. Now, it is also sometimes possible that there is no, so suppose one of the red points was here, then there would be no line which divides this plane into two regions where one all points or blue points are on one side and red points on the other side. That can also happen, in which case we could perhaps try to find the best line still which minimizes the errors. So, this this is a sort of can be rephrased as an optimization problem. So, what are we looking for? We are looking for a line, right. So, and what is the equation of a line? Well, the equation of a line is always sort of y is equal to a x plus b, unless it is a vertical line, right. So, this a is the slope and b is the y intercept. If it is a vertical line, then this will not detect it, but maybe you can just separately check if all the points are separated by a vertical line or not by just looking at the x coordinates. If all the x coordinates of the blue points are less than all the x coordinates of the y points of the red points, then you know that they are separated by a vertical line. So, let us forget about vertical lines, let us look for a line that is not vertical. The vertical case is easy, which we can do before we start this process. So, we are looking for this line, and what we want to do is we want to find out if we want this line to have the property that the blue points are above the line. So, what does that mean in terms of x 1 and y 1? So, above means the y coordinate should be more than the y coordinate on the line, which means y 1 should be greater than a x 1 plus b 1, right, plus b, there is no b 1. yeah, and y 2 should be y 2 should be greater than a x 2 plus b and so on, and then y k should be greater than a x k plus b, and just going from yesterday's experience, let me try to save this, I guess. Okay. And then we want more conditions for the red points. We want y k plus 1 is less than a x k plus 1 plus b, y k plus 2 is less than a x k plus 2 plus b, and so on, and y n is less than a x n plus b. So, these are the conditions we want. Yeah.
X and y n, right? The red last coordinate.
Yeah, x and y n, sorry. So, the n points. So, we want this kind of separation. Now, we will see when we study, I have not really introduced linear programming, but in linear programming we generally do not allow the strict inequalities, we put greater than or equal to. So, what we will do is we will introduce one more parameter called delta. So, we will try to do in fact a little better than this, we will try to actually introduce some sort of region around the original line in which there will actually be no points. So, this region will have height plus or minus delta. So, what we will say is that y 1 is greater than or equal to plus plus delta plus delta plus delta, and here we will put minus delta minus delta minus delta. And what we want to do is we want to maximize delta. And we will see when we look at linear programming problems in general that you can also detect whether there is a solution or not using various algorithms related to linear programming. So, what is happening is that this separation of points problem has been rephrased as a problem where you have certain constraints which are inequalities involving linear expressions. What are the variables here? A and B are the variables, right, not x 1 y 1, those are fixed points. So, this is a slightly confusing example in that sense. A and B are the variables which we want to find, right. So, we want to optimize A and the values of A and B, and so and we want to find it so that it has a largest region around it with no points, and all the blue points are on one side of that region and all the red points are on the other side. So, this is an example of a linear programming problem. So, you have inequalities which are linear in the variables, in this case the variables are a, b, and actually delta also. Okay. So, variables are a, b, delta, and we have n linear inequalities, and we want to maximize delta, which is called the objective function. So, this objective function itself in general is a linear function of the variables, in this case it is just one of the variables delta. So, here is a problem of point separation reparameterized as a problem of optimization under constraints which are linear inequalities and the optimization of a linear objective function. So, let us look at some more examples before we go to the general case, and
excuse me, sir.
What? looking for the new page. Ah, yeah. It keeps moving. No, maybe not. Anyway, okay. So here's another problem which very nicely, and this is itself a large class of linear programming problems, which is called network flow. And this class of problems is huge in both applied and pure mathematics. There is this book, famous book by Ford and Fulkerson called Flows in Networks. If you get a chance to look at it, it's a beautiful book. So you have a network. So let me just give you an example. So for example, you have a source. This could be a factory where goods are produced, and you have a target, which could be a place where these goods have to be transported to. And this is an example of, say, a transportation network. So you have various nodes in between through which you can ship your goods. So let us just call them A, B, C, D, E. Okay, so in this case I have 5 nodes in between, and we have arcs joining these nodes. And these arcs you can think of as transportation routes, but so for example, these could be so this could be some place where military hardware is produced. T is the place where you need to transport them to fight a war, and these could be airports in between through which you have to transport it, and you cannot fly directly maybe because it is too far. So these things may have capacity. So this route you can only send 3 units say in a given time. This route you can send 1, this route you can send 1. Let us say you have some, okay, so 4, 3, 4, 1. Okay, so each arc has a capacity, and now your problem is, what is the most I can transport from S to T, and how should I do it? How much should I send? So what you do is you put a variable. So I will say X S A is equal to the amount to be transported through the arc S A. D to T, let us put some capacity there. Okay. Yeah. So everything has to have a capacity, amount to be transported. Sometimes some nodes have, some arcs have infinite capacity, then you can just leave it out, but let us say they have a positive capacity transported through the arc S A. So how much you will transport along this thing, right? So and then we will have X A B amount to be transported through the arc A B, etc. So now this network flow problem can be phrased as, so what are the constraints that we would have? So one constraint is the capacities. So we would say that X S A well lies between, let us say, -3 and +3. It is important to allow backflow also. Sometimes you can increase capacity. So maybe the capacity of going from here to here is high, and then you want to move things sort of in both directions to optimize your flow. So we will allow these flows to be positive or negative. So similarly, we would have one equation for each arc. So we will have X A B lies between -1 and +1, X C D should lie between -4 and +4, etc. And in these kinds of problems, there might also be a constraint that you can't store anything at any of the arcs. So then what you should say is that whatever goes out of an arc should come into the arc at the same time. So let us look at, for example, the arc at A. So we will have something like, what is coming into A is X S A, and what's going out of A depending on my orientation, right, x A B. Let us not have different variables x A B and x B A. X A B is what is going from A to B, and if it is negative then it will be going from B to A. So, let us not duplicate things, and what else is coming into A? Okay, so x S A is coming into A and x A B is going out of A. So, we should not write it like this. So, we should write whatever is coming in is the same as what is going in. So, I will write it as is equal to x A B plus x A D, right. So, if I look at the node B, what should the equations be? X S B plus x A B, we will not keep B A, is equal to x B E. Okay, so, in that way we can write down. And then what do we want to maximize? We want to maximize the stuff that is going into T or the stuff that is coming out of S. It has to be equality. Say we can't store anything at these nodes, whatever comes in has to go out. So, yeah, you can't send 3. So, then these two will definitely put a constraint that you cannot send more than 2 on this. So, that much capacity will be redundant, right. So, you get a bunch of equalities, a bunch of inequalities, and the objective function is maximize z equal to, let us say, x A S A plus x S B plus x S C. Because nothing is being stored at the intermediate nodes, you will find that this is also the same as x D T plus x E T, everything goes through, right. So, this is another example of a linear programming problem. And one more problem we look at is again line fitting, but not separating. So, I have just one type of data and I want to fit a line. So, again we are just given some points. Yeah.
So, what was the role of delta in the first slide?
In the first slide, yeah, let me go back. Once I figure out how to go back. Oh, yeah. So, this delta, okay. So, one of the things is we did not want strict inequalities, because they cause some problems. When you are talking about strict inequalities, you may not attain the maximum value. So, your problem, your linear programming problem becomes somewhat difficult. So, what you do is you replace them by something with an equality, but with a weak inequality. Okay, so now we have a weak inequality, but this delta is sort of this gap here. So, this height difference here is delta and this height. So, you take your line that you want, you draw a line at a height delta above it and another line at a height delta below it. And what we are saying is that all the blue points should be above that line which is a line delta above it. So, we are sort of strengthening the problem, but we are not specifying the value of delta. So, we are looking for a line, the best line that separates it, and this best line is defined by the fact that we should be able to draw lines above and below that line which still separate the blue and red points and maximize that. Okay, so, what you must try to do in this problem is to maximize delta. It is possible that there is no line separating the blue and red points, in which case you will not have any non-negative values delta which have this property. But you could still try to maximize delta as a negative number, that is find the least negative value of delta, and that will give you an approximate solution. But you could also insist that delta is greater than or equal to 0 and try to maximize it. I hope that answers your question.
Yes, thank you, sir.
Okay. Yeah, of course, please feel free to interrupt at any time and ask questions. Okay. So, now analogous to that, separating again this is a finding a line problem, but now we just have a bunch of points and we want to find the best linear fit. So, this is often a problem in linear regression, where we try to sort of reduce the least squares error. But one of the problems with least squares error is that it is highly sensitive to outliers, because when you have a big error you are squaring it, and so it becomes even bigger, and so it lacks what statisticians call robustness. Okay, it can get thrown off, like maybe you have one erroneous observation or one outlier, it will completely distort your line, the least squares thing. So, another approach to fitting a line rather than using least squares is to use absolute value. So, let me formulate the problem exactly. So, we are given points x 1 y 1 x n y n in R squared, and what we want to do is again find a line. So, find a line y equals a x plus b, so that it is close to all these points are close to the line. So, what we want is y I is close to a x I plus b, yeah, or in other words we want this error to be very small. So, what we want is that this thing should be small. So, let us but it could be that y I is greater than a x I plus b or y I is less than a x I plus b. So, we will just take this difference y I minus a x I plus b absolute value, and we will take this sum I goes from 1 to n, such that this is minimum. Okay, so, just for context, there is another problem which is the least squares minimum. So, in that case you are trying to minimize summation I goes from 1 to n y I minus a x I plus b squared. So, this is called the least squared fit, and what we are doing is the absolute value fit. So, this least square fit is something I will not talk about right now, that has a different technique, and here I am going to talk about this fit and how to find the best line. And this becomes a problem of optimizing a linear objective function under certain linear constraints. So, here is the linear program. So, we will introduce some more variables now. So, we will introduce the errors. So, let us say y I is equal to a x I plus b plus e I. So, these errors could be maybe I want to say okay, let me just state the program and then we will analyze it. So, here is the formulation. So, optimization problem is minimize E1 plus E2 plus En subject to the constraints E1 is greater than or equal to a x 1 plus b minus, let us just write it for the E I is greater than or equal to A x I plus b minus y I for I equals 1 to n, and E I is greater than or equal to minus of this A x I plus b minus y I for I equals 1 to n. So, what this means is that E I is greater than or equal to A x I plus b minus y I in absolute value, the absolute value of the error. So, and so now in this program the variables are E 1, E 2, E n, A and b. Okay, the x I, y I are fixed quantities, they are the points that were given. And in an optimal
should be less than. EI should be less than or equal to in the first inequality.
EI should be EI should be absolute value of EI should be greater than or equal to. So, in the second one it should be less than or equal to, you are right. Okay, so now suppose you have an optimal solution to this, then so you know find so the variables are E 1, E n, A and b, and our goal is to really find A and b. Now, suppose you find an optimal solution for this, then if any of these EIs is positive, then you should be able to reduce it further and get a better solution. So, in an optimal solution it will turn out that these EIs are actually 0. So, otherwise you could decrease it, and then the resulting A comma b will give you the best fit line. So, so these are 3 examples of how you know common sort of problems, 2 of them with analysis of data and the fitting a line and separating points, and one of them is sort of operations research. These problems are linear programming problems. So, yeah.
This way of construction will lead to a large number of constraints according to the
One constraint for each variable, 2 constraints for each variable. Yeah.
2 constraints for each data point.
Yeah, sorry, for each data point. Yeah.
So that means if you have n data points, it will be too much for.
Not it's not as bad. We'll see. I mean, you can run pretty large. You can run pretty large problems of this kind. So yeah, we can think about the complexity of this based on the number of variables is also the number of points. So if you had like 1 million points, then you would have 1 million variables and 2 million constraints. And you will see you will have to add slack variables, so you will actually have something like, yeah. So it's still yeah. So the number of equations and constraints is sort of a linear function of the number of points, and still can run for somewhat largish things. Okay, so these are just examples, and now let us take a toy problem and see how we solve it using the simplex method. And it kind of uses what we talked about of linearly independent vectors from a set of vectors. So that is the basic idea that is behind these things. So let us talk about the simplex method now, and again I will just introduce it using an example. So let us say we have the following optimization problem. maximize the objective function 3x1 minus 2x2 subject to the equations 2x1 minus x2 is less than or equal to 4, x1 plus 3x2 is greater than or equal to 5, and x2 is greater than or equal to 0. So, this thing is called the objective function. These are the constraints. Okay, so, the objective function is linear in the variables are x 1 and x 2, and the constraints are inequalities, linear inequalities in the variables. And here in this case there are only two variables, you can try and plot this region which you get, and usually this is how linear programming is introduced. We just have two variables, we draw something and we so, but let us not do that. I am sure you can all do that, maybe try to do it and see how to do it, but let us think more sort of algorithmically on how we would solve such a problem even if it had many variables. In fact, the first thing we will do is we will increase the dimension of this problem. So, so the most common way of thinking about these is to replace inequalities by equalities and require all the variables to be non-negative. So, that is called the equational form of a linear program. So, here this is an inequality, we want to turn it into an equation. So, what we are saying is x 1 minus 2 x 2 is less than or equal to x 4. That is the same as saying that 2 x 1 minus x 2, and let us just introduce a new variable called x 3 is equal to 4. That is, and we will also require that x 3 is greater than or equal to 0. So, this is called a slack variable. So, there is some slack in 2 x 1 minus x 2, it is not quite x 4, we want to make it equal. So, we introduce a variable that eats up that slack, that space that is there, and that variable require it to be non-zero, non-negative. So, this is called a slack variable. And we can do the same thing here, but now it is greater than or equal to 5. So, we can put a negative slack variable. So, what we can do is instead of saying that the variable is less than or equal to 0, we can put it with a minus sign. So, we could say x 1 plus 3 x 2, and now the slack is independent of the old slack. So, let us not call it x 3, let us call it x 4 minus x 4 is equal to 5, and now we will also say x 4 is greater than or equal to 0. So, this is also a slack variable. And we have this condition that x 2 is greater than or equal to 0, but we do not have this condition that x 1 is greater than or equal to 0, right. But we will artificially create that. We will write x 1 as y 1 minus z 1, where y 1 is greater than or equal to 0 and z 1 is greater than or equal to 0, right. Any real number can be written as a difference of two non-negative real numbers. And so, we will just replace this by y 1 minus z 1. So, we will replace this by oops, uh, 2 y 1 minus 2 z 1, and here also we will replace it by y 1 minus z 1. Right. So, now our and so we have y 1 greater than or equal to 0, z 1 greater than or equal to 0. So, we have 1, 2, 3, 4 variables, 2 equations, all the variables are required to be non-negative, and what is our objective function? Yeah, go ahead.
Why are you replacing x 1 variable y 1 and z 1?
Okay, so what I am doing is I am reducing this formula to something in a standard, this problem to a problem in a standard form, and when we do the simplex method, you will see that we require the problem to be in a standard form. So, in the standard form, it is called the equational form. All the you only allowed linear equalities and all the variables are greater than or equal to 0. So, here we have, if we had x 1, we had not replaced x 1 by y 1 z y 1 minus z 1, then that x 1 could be greater than or equal to 0 or less than 0. So, it would be allowed to vary all over, but we only want our variables to be non-negative. Yeah, so this maybe I am doing it backwards, but I am reducing the problem to a standard form. So, I will explain what that standard form is in general the moment I finish this example. So, so is that okay? Yeah.
Okay.
Okay, so now let us look at this objective function. I need to also rephrase this, right. So, the objective function usually it is just called z. Z is equal to 3 x y 1 minus 3 z 1 minus 2 x 2, right, because x 1 is y 1 minus z 1. This is the and at least, okay, even if you do not know why I am doing it, you will agree that this problem is the same as the original problem. I have to find y 1 z 1 x 2 x 3 non-negative such that these two equations hold, and I have to, and the objective function 3 y 1 minus 3 z 1 minus 2 x 2 is maximized. Once I solve this problem, I can get back by x 1 by just taking y 1 minus z 1. Is that okay? So, this is what is called a linear program in equational form. So, let me so linear program in equational form. So, this will be our starting point. We will assume that whatever linear programming problem we are given is in equational form. So, so what we are given is A is some m by n matrix of say real with real entries. So, this is going to be the matrix of coefficients. X vector x is going to be a vector of variables x 1, x 2, x n, and we are going to have a vector b, column vector b 1, b 2, b n, and these are sort of the this is in R n, and we are going to have the coefficients of the objective function C 1, C 2, C m. So, this is C transpose, I write it as a row vector, C is a column vector. So, this is the data, and the problem is maximize C transpose into x. So, what is this? This is just C 1 x 1 plus C 2 x 2 plus C m x m. C, this should be n, I guess, yeah, C n x n. This should be m and that should be n. Maximize this subject to the constraints A x is equal to b and x is greater than or equal to 0. By saying that a vector x is greater than or equal to 0, this just means that x 1 is greater than or equal to 0, x 2 is greater, each component is greater than or equal to 0, and this just is C 1 x 1 plus C n x n. Okay, so, this is the equational form, And in this previous example, we have actually created an equational form out of the form which was not equational. So, in this example, A is the matrix 2 minus 2 minus 1 1 1 oh sorry yeah 1 4 is also there. So, 0 1 minus 1 3 0 minus 1. X is the matrix y 1 z 1 x 2 x 3 x 4, it is the column vector. What is B? B is just 4 5 and C transpose is the objective function, right. So, it is 3 comma minus 3 comma minus 2 comma 0 comma 0, right. So, what I have tried to explain in this example is that given any general linear programming problem which involves inequalities and some variables which are not required to be non-negative, you can always replace it by an equivalent problem which involves only equalities and all the variables are required to be non-negative. Okay. Also, they could have been something like x 2 less than or equal to 0. In that case, what I would do is I will just replace x 2 by minus y 2 or something like that. I just change the variable sign and then that would be non-negative and then I could just So, you can always turn any linear programming problem. So, the 3 examples that we saw before, many of them involved variables which were not required to be non-negative and they involved inequalities. So, you introduce slack variables, you split up variables into differences and you get it into equational form. Now, this comes at the cost of increasing the number of variables and increasing the number of constraints, but that is okay. It then feeds into a very standardized algorithm which works very fast. So, that is the idea. So, this is the equational form that we will start with. So, so let us do one problem by hand sort of and then we will analyze how it works. We will use the simplex method. So, so here is a problem that I sort of prepared. So, maximize 3 x 1 minus 2 x 2 subject to 2 x 1 minus x 2 less than or equal to 4, x 1 plus 3 x 2 greater than or equal to 5, x 2 greater than or equal to 0. Okay, this is the same problem, right? Yeah, okay, good. So, we write it in equational form. Yeah. Wait. So, now let's I think I am going back in my notes. Let's not redo this thing. So, yeah. Just want to say something about the related geometry. So, we started with this problem in 2 variables and then we ended up with a problem in 5 variables, right. So, the dimension blew up, but I will just sort of, so you can't usually draw pictures because the dimension blows up, but suppose you had only say 3 variables and maybe 1 equation, then you could sort of visualize this problem. So, for example, if you had x plus y plus z equal to 1 or something, this is your equation, then x greater than or equal to 0, y greater than or equal to 0, z greater than or equal to 0. So, what will the region, the constraints look like, the feasible region, right. So, you would just take this vector 1 0 0 E 1, then you would take the vector 0 1 0 and you take the unit vector in the z direction 0 0 1, and what you would do is you would sort of so there is a plane. So, these all lie in the plane x plus y plus z equals 1. These are 3 points, and so they uniquely determine this plane x plus y plus z equals 1. But saying that each of these variables is greater than or equal to 0 is the same as saying that you must lie in the region of the plane that is inside the positive what is it called, octant, right, the positive eighth of 3 dimensional space, where all the 3 coordinates are positive. So, this is your feasible region, this gray stuff. In this case, it is just a triangle, and this is the best I can do drawing in 3 dimensions, because there are only 3 axes. So, but say if you had one more equation, then this would be reduced to a 1 dimensional thing and end up becoming a line somewhere, right. So, so anyway, so the geometry is something like this, and the corners are where one ends up focusing, these 3 points. Okay, so in general, if you have 2 variables, your feasible region in those 2 variables will look like some polygon, a convex polygon, and it is the corners where your linear function, objective function will be maximized. So, yeah. So, we will make some 2 more simplifying assumptions, which I will try to convince you are not very serious. So, what is the form of the problem? The form of the problem is A x equal to b, x greater than or equal to 0, maximize C transpose x. Okay, it could be minimize C transpose x, but then I could just change that to maximize by replacing the coefficients of C by their negatives. So, then that gets maximized. So, we will always we will think of it as maximize, and we will think of it as linear equations, and we will think of the variables as being non-negative. So, that's sort of now going to be set in stone, all the problems when we look at it. Okay. So, we will make 2 more simplifying assumptions. One is that the equation A x equal to b has at least one solution. It is a linear equation. If it has no solutions, then of course, there are no solutions and there are no optimal solutions, right. At least one solution, and we will also assume that there are no redundancies in the conditions. So, we will assume that the rows of A are linearly independent. That means, the equations that we have do not depend on each other. You cannot eliminate one of the equations by doing something with the other equations. So, you can always remove redundant equations. Okay, so these are the 2 assumptions. So, what this means is that the rank of A is the number of rows, which is m. Okay, and now we will talk about these so called corner points, right. So, how do they show up in this thing, and they are what are called basic feasible solutions. So, I should introduce this word feasible. So, a point x in R n is said to be a feasible solution if it satisfies the constraints, if A x is equal to b and x is greater than or equal to 0. Okay, so, it is not a final solution to your problem, but it is a possible. So, it is the set of points that satisfy all the constraints. So, in this picture it would be all the sets in the I have disabled that, yeah. So, all the points in this gray triangle, right. So, this is the feasible set. and among these we look for special ones called the basic feasible solutions. So, yeah. So, so we'll say that a subset B. So, we have this matrix A. So, in this example we had this matrix A, which was a matrix with 2 rows and 5 columns, right. And we will look for columns that are linearly independent. So, in this case I guess any 2 columns are linearly independent, no columns are dependent on each other, no column is a scalar multiple of the other, right. So, we will say that a subset is basic if so B is a set of columns. So, it is a subset of what are the columns? The n columns. So, it is a subset of 1 to n is said to be basic if the matrix A subscript B. What this means is that this is the matrix obtained from A by selecting the columns corresponding to B. So, submatrix consisting of columns from the set B. So, for example, if A is, so maybe I take an example where some of the columns are dependent 1 5 0 1 5 3 4 6 0 1 3 5 6 and let us say B is 2 comma 4. So, what is A subscript B? So, for A subscript B you must take the second column and the fourth column and take the submatrix. So, that is 5 4 1 5. Now, these 2 columns are not linearly dependent, the second column is not a linear multiple of the first one. So, this matrix is non-singular. So, it is said to be basic if A B is non-singular or it has rank equal to m, has independent columns. Yeah, so we have to assume here that B is of size m. If B has m entries and this has independent columns, and okay, so that is just a so now we have this set 1 to n and certain subsets give us independent columns. Okay, so what is so special about these basic things? So, what is special about these basic things is now each column here corresponds to a variable, right. Remember in this there would be 5 variables. So, let us just call them x1, x2, x3, x4, x5. So, so we have this equation A x is equal to B. Then what we are saying, we can write this like this. So let us just look at this. So, we have, so the equation is x1 plus 5 x2 plus 3 x3 plus 4 x4 plus 5 x6 is equal to, I need some B, right. So, let us put some B. Something. Okay, so is equal to 2 and x2 plus 3 x3 plus 5 x4. Oh, this should be a 6. Oh, there is no x6 plus 6 x 5 is equal to 4. So, we have these two solutions, not these two equations, and what we can do is now we can rewrite this in the following form: 5 x 2 plus 3 x 3 is equal to 2 minus x 1 minus 4 x 4 plus minus 6 x 5. And we can write it as x 2 plus 3 x 3 is equal to 4 minus x 2 minus 3 x 3. Oh, sorry, minus 3 is in the solution. So, I should not 3 is in the basic set, minus 5 x 4 minus 6 x 5. X 2 is also not there, right? Yeah, x 2 plus 3 x 3 is 4 minus 5 x 4, yeah. Okay. Okay, so, but now because this matrix is non-singular, we can solve this in terms of x 1 and x 2 and x 3. So, what we can do is we can solve it and write that you know. So, if we, so what we
Hello.
get is, yeah.
Sir, I think here x4, x2 and x4.
Oh, 2 and 4, sorry, I changed it to 2 and 3, okay. Yeah, so 2 and 4, so I should write 5 x 2 plus 4 x 4, right? Yeah, no, but here I said b is 2 comma 4, so let us not. Yeah, 2 and 3 are basic, but I mean there should be some consistency. Maybe it is easier to change this 4 to a 3. Okay. So, anyway, so let us just cheat here and change this. So, what we have done is we have been able to, so then A B is what? Now, I have to change this also. So, 3 3. Okay, but now these two equations are independent. So, I can solve for x 1 and x 2. So, in fact, I can solve, I can write x 2 is 4 minus 5 x 4 minus 6 x 5 minus 3 x 3 and then substitute that in here. And so, I can write x 2 is something in you know, in terms of x 1 something x 4 something x 5, right. So, and some constant. So, I can write it as maybe to be more specific, I can write it as some constant C 1 minus A x 1 minus B x minus or plus, it does not matter, x 4 minus C x 5, x 3 is maybe d 2 minus A 2 x 1 minus B 2 x 4 minus C 2 x 5. So, I can write x 2 and x 3 in terms of the other variables, and then whatever. So, the what is happening is that I had this system of linear equations, it does not have a unique solution, and that is what makes this linear programming problem interesting. There are many feasible points. This is some sort of hyperplane in 5-dimensional space. It is going to be a 3-dimensional subspace of 5-dimensional space, because there were 2 constraints. And in this 3-dimensional subspace, I am sort of finding a parametric form. If you tell me x 1, x 4 and x 5, I will find you a definite point on this space, right. So, I have parameterized the space in terms of the variables that are not in B, right. What we are really doing is that we are saying, yeah. So, can express. So, I will call these variables x 2 and x 3, I will call them basic variables, the ones which correspond to B, and the other variables the non basic variables. So, expressing these are the non basic variables. So, what you can do is, because this matrix is non singular, you can express the basic variables in terms of the non basic variables, and you can put whatever values you like for the non basic variables and get values for the basic variables, right. So, so for example, the easiest thing to do would be to put that the non basic variables are 0 0 0. Okay, so maybe
A1, B1, C1 you expect to be non-negative. That's why
yeah, so D1 and D2 should be non-negative. So, let us see what happens in this example. So, in this example, I think we should just solve it and see what these equations are.
So my question is, why you put the minus times A1 minus times B1?
It can put plus. No, it's just because I was sort of, yeah, it doesn't matter. Minus is easier to write than plus. So, yeah.
Sir?
Yeah.
So basically, the basic variables depend upon the choice of set B only. There can be many choices.
So, yeah, so you choose a set B such that A subscript B, that is the column selected submatrix, is non singular. So, then you take the variables corresponding to those columns and you see if it is so then you can express those variables in terms of the remaining variables, right. So, let us just see what happens in this example. So, here if I put so what I am going to do is I am going to set the non basic variables, that is x 1 equal to x 4 equal to x 5 equal to 0. Then the equations I get are 5 x 2 plus 3 x 3 equals 2, x 2 plus 3 x 3 equals 4, right. Set non basic variables to be 0. So, I am setting x 1 equals x 4 equals x 5 equals 0, then what I get is 5 x 2 plus 3 x 3 is equal to 2 and x 2 plus 3 x 3 is equal to 4. So, now I can easily eliminate x 3 from this by taking the difference. So, I get 4 x 2 is equal to minus 2, right. So, x 2 is equal to minus half. This is not good because I wanted x 1, I wanted all the variables to be non negative, right. So, this is not non negative, right. So, this is a bad place to start. So, maybe I should start with 2 comma, what was it? 4. So, let us start with 2 comma 4 instead. So, let us try, we will see how to find your first basic good basic variable, but let us just try 2 comma 4 instead. So, let us try, so maybe I should copy this from here. No. This, oh, okay, there we go. So, this is the problem that we are dealing with. So, yeah, so let us try, we did 2 comma 3 and that did not work. So, let us try 2 comma 4, damn it, 2 comma 4. Okay, so in this case now we are looking at, so we will set x 1 equals x 3 equals x 5 equal to 0, right. And we also have the equations. So, the equations are given here. So, we can easily express these x 2 and x 4 in terms of those things, and the equations we will get is x 2 5 x 2 5145. Thank you. I just copied this from the previous thing without changing. Yeah. So, now it is 45. So, what we get is let us just. So, we get so what must we do? We must write x 2, right, and I am assuming that these x 1, x 3, x 5 are 0. So, what we get is 5 x 2 5 x 2 plus what is the other one 4, right, 4 x 4 is 2 and x 2 plus 5 x 4 is equal to 4. Actually, in my thing I had 14 and 7, but okay. So, let us see if this works. So, now okay, so x 2 is equal to 4 minus 5 x 4. So, 5 x 2 is 20 minus 25 x 4 plus 4 x 4 is equal to this is also becoming negative. So, actually positive only minus 5 plus this is okay. So, this is both are negative. So, this is minus 21 x 4 is equal to minus 14 18. So, x 4 is equal to 18 by 21, which is greater than or equal to 0, and x 2 is equal to 4 minus 5 x 4. This looks very close, 90 by 21. Okay, this is slightly more than 4, right. So, this is negative. Yeah. So, okay. So, just for 18 into 5 is 90, right. Okay. So, just for the sake of yeah. So, this is also not a basic feasible solution. Okay, but now I realize that in the example I prepared I had b equals 14 comma 7. So, suppose instead the problem had, so but this shows you that you cannot take any basic subset and get a feasible solution. You need to find to start with a basic subset which gives you a feasible solution. So, if instead of 2 and 4 I had 14 and 7, which is actually what I had prepared in my yes.
So, even though they are not satisfying the constraints for being positive, still they are basic one.
They are not basic feasible solutions. That set is basic in the sense it gives a basis for the columns, but you do not get a feasible point in your thing. So, if we had this for example, then we would be able to yeah.
We can change x1, x3 some other.
Yeah. So, you can keep trying till you find something that works. Yeah. Correct. So, you can keep trying till you find. I will tell you how to solve that problem also. So, that problem will itself become an auxiliary linear programming problem. So, yeah. So, let's just so I just do not want to keep spending time trying out different things. So, here is an example that I worked out before. So, let us put 14 and 7 and then we get x 2 is equal to so we get x 2 is equal to 7 minus 5 x 4 and so then let us just erase all this. And so we will get x 2 is 7 minus 5 x 4, let us substitute that. So, we get 5 into 7 minus 5 x 4 plus 4 x 4 is equal to 14, which is 35 minus 25 x 4 plus 4 x 4 is equal to 14. In other words, 35 minus 14 is 21, is equal to 25 minus 4 is 21 x 4. So, x 4 is equal to 1, because this was a carefully prepared example, and then we can solve x 2 is 7 minus 5, which is 2, and both these are greater than or equal to 0. So, here is the definition. A basic feasible solution is a feasible solution x in R n for which there exists a basic subset Basic means it is a subset of size m, which such that the submatrix is full rank, B of 1 to n such that firstly the variables which are not in the basic set are 0. Okay, the variables that are not in the basic set are 0, that is all. So, this taking b equals 2 comma 4 in this example, what I get is in this example, what is the basic feasible solution? What is the vector I should be looking at? In this example, I am setting x 1. So, the basic set is 2 and 4. So, 1, 3 and 5 have to be 0, and then the others you solve in terms of these things, setting them to be 0, and what you got is x 2 is 2, x 1 is 1, is a basic feasible solution. Corresponding to b equals 2 comma 4. So, you start with this subset of size 2. Okay, so, so now the linear programming simplex algorithm rests on the following theorem. So, so consider the linear programming problem in equational form. Maximize C transpose x subject to A x equal to b, where A is an m by n matrix. We assume that A is full row rank, and we also have this constraint x greater than or equal to 0. And yeah, then the first statement is that if there is at least one feasible solution, That means, if there is at least one point which satisfies one vector x which satisfies these conditions, forget about the maximization. And the objective function is bounded, then if either of these conditions do not hold, then there is no optimal solution, but the converse is true, then there is a optimal solution. There is an optimal solution. I am not saying that it is unique, but there is an optimal solution. This is essentially a topological argument. This, so the set of values that the objective function takes is going to be bounded above, and it is given by closed conditions. So, it is going to have a maximum value, it is going to attain its maximum. And the second point is that if an optimal solution exists, then there is a basic optimal solution. So, I am not saying that all optimal solutions are basic, but if an optimal solution exists, then there is a basic one, is a basic optimal solution. So, let us go back and look at this thing. So, this is your feasible set, the gray region, and you are trying to maximize something, then maybe it is maximum everywhere along say this edge over here. Okay. Then it will be maximum at one of the corners. The point is, it cannot be maximum at some point somewhere in the middle, because somehow intuitively speaking the objective function is linear, and so when you move away from this, at least in one direction, it will increase. You sort of move in the gradient of that objective function, it will increase, right, unless the objective function is constant, in which case it does not matter. So, there will be some direction in which the objective function increases. Of course, the objective function should not be constant on this hyperplane, on this subspace, not subspace, whatever, this hyperplane. Yeah. So, if the objective function is not constant along this hyperplane, then it will increase along some direction. If it is constant along this hyperplane, then you can choose any point and it will be optimal. So, you know, the possibilities in this picture are either the whole thing is optimal, or one of the lines is optimal, or one of these three red points is optimal. Those are the only three possibilities, but in each case one of these corners is optimal, right, because the whole plane is optimal, then all three corners are optimal. If this line is optimal, then both ends of the line are optimal. So, what we are saying is that it may not be that the optimal solution is unique, but you just want one optimal solution, then just look for it among the basic solutions. So, the way the simplex method works is that you sort of jump from one basic feasible solution to another while trying to improve the value of the objective function. So, if you are trying to maximize it, you keep trying to jump while increasing the value of the objective function. So, let us just go back and do an example, and I will sort of where is the so let us look at this example. Maximize x 1 plus x 2 subject to the conditions x 1 minus x 1 plus x 2 is less than or equal to 1, x 1 is less than or equal to 3, x 2 is less than or equal to 2, and x 1 greater than or equal to 0, x 2 greater than or equal to 0. So, the first thing we should do is we should put it in equational form. So, we will introduce here one slack variable we will say x 1 plus x 2 plus x 3 is equal to 1. We will introduce another slack variable here, saying x 1 plus x 4 is equal to 3, and we will introduce one more slack variable here, saying x 2 plus x 5 is equal to 2. And we will require all these variables x 3 greater than or equal to 0, x 4 greater than or equal to 0, x 5 greater than or equal to 0. And our objective function does not involve these variables x 3, x 4, x 5, it only involves x 1 and x 2. So, in this case what we are saying is A is the matrix minus 1 1 1 0 0, 1 0 0 1 0, 0 1 0 0 1, B is 1 3 2, C transpose is x 1 x 2 0 0 0, x 1 plus x 2, right. So, and now we should start with the basic feasible set. So, in this case we actually, if you look at this matrix, there is this 3 by 3 sub matrix which is clearly non singular, it is just the identity matrix, and these are actually the slack variables. So, this always happens in these kind of examples where you just have inequalities and all the variables are greater than or equal to 0, just the slack variables will, you will get one slack variable from each equation, and that gives you a basic feasible solution. So, what we will do is we will take B equals 3 4 5. Of course, my variables matrix is x 1, x 2, x 3, x 4, x 5. So, B equals 3 4 5, and so we can express x 3, x 4 and x 5 in terms of the remaining variables. So, we will write this down in the form of what is called a tableau. So, a tableau, you know, the word English word sort of means arrangement, say in a play or in a dance or something, of people all, you know, posing in a certain way, which looks, which makes it, which expresses something. So, this we will try to express this by saying that, okay, these are our basic variables, this is how they behave, this is our objective function. So, it is all about just writing it down nicely. So, our basic variables are x 3, x 4, x 5, and we can express them in terms of the other variables. So, let us do that. So, let us write down the tableau. So, so we have x 3 is equal to, so x 3 is 1 minus 1 plus x 1 minus x 2. Right, x 3 is 1 plus x 1 minus x 2, x 4 3 minus x 1, x 5 is 2 minus x 2, and we will also write down the objective function. We need to keep an eye on the objective, right. So, z is equal to, it was just x 1 plus x 2, right. And these things are positive. So, actually they just need to be non-negative. So, we have a basic feasible solution here, right. So, our basic feasible solution is 0 0 1 3 2, and what is the value of the objective function? 0, because the only variables that enter the objective function are the non-basic variables, and they are set to 0 in this basic feasible solution. So, we are very far off from finding the optimal solution, but look at this objective function. If we were to either increase x 1 or x 2, we would increase z, right. So, let us try to increase one of them. So, we could either increase x 1 or we could increase x 2. You can choose either way. So, let us say, just to be contrarian, we will increase x 2. So, let us try increasing x 2. So, this what I am going to do is called a pivot step. So, what we are saying is that okay, we have this the objective function, it looks like if we increase x 2 we can improve the objective function. So, try increasing x 2 and only x 2. So, what I am saying is keeping x 1 equal to 0. If you try increasing both, things get a little complicated. So, let us just try increasing x 2. So, I am keeping x 1 equal to 0, and what are the other constraints? The constraints are x 3, x 4 and x 5 should all be greater than or equal to 0. So, if you look at this first equation, we want x 3 to be greater than or equal to 0, x 1 is 0 and we are increasing x 2. So, what we get is this first equation gives 1 minus x 2 should be greater than or equal to 0, which means that x 2 should be less than or equal to 1. What about the second equation? Second equation does not involve x 2 at all. So, it does not give any constraint on x 2. The third equation tells us that x 5 is 2 minus x 2. So, we are saying that 2 minus x 2 should be greater than or equal to 0, which means that x 2 should be less than or equal to 2. So, we cannot increase x 2 beyond the value 1, right. The moment it goes above 1, x 3 becomes negative. So, then we will be outside the feasible set. So, this is the tight, we can't increase it beyond this. This is the most we can increase x 2. So, let us increase x 2, we will increase it to x 2 equal to 1, and what we will do is we will add x 2 to the basic set and we will remove. So, this constraint came from the first equation x 3. When we put x 2 equal to 1, this x 3 actually becomes 0. So, we can move x 3 out of the basic set. So, what you do is the pivot is x 3 enters x 2 enters, x 3 leaves. So, we will now take b equal to x 2 enters. So, we had 3 4 5, now we will take it to be 2 4 5. So, what I need to do is I need to write x 2, x 4 and x 5. No, some, yeah, you can ask.
You said some variable is leaving and another variable is entering.
Correct.
I could not understand that reasoning.
So suppose I set x 2 equals 1,
Okay.
then remember we are keeping x 1 equal to 0. So, if you look at this first equation, when I put x 2 equals 1, x 3 becomes 0. Now, whenever we talk about a basic feasible solution, we are saying that the non-basic variable should be 0. So, I can remove x 3 because now that x 3 is becoming 0 and put x 2 equal to 1. So, what I am going to say is I am going to make x 3 leave. So, the variable that leaves is the variable from which, so this thing gave us this condition. The constraint x 3 greater than or equal to 0 gave us this condition. So, when I maximize x 2 to use up all the space that this condition gives me, this thing becomes 0. So, that is the variable that will leave. So, in each pivot step, one variable will leave the basic set and another variable will enter the basic set. It is exactly a sort of exchange of basis elements from one basis. So, you have one basis and you are going to change it by removing one vector from it and adding another vector. So,
In this step, the x 1 leaves, you are saying that
x 1 enters, right? 3, 4, 5 are basic. So, now
x 2 is
x 2 enters, x 2 enters, x 3 leaves.
x 3 leaves.
Yeah,
So
x 1 is kept 0, I do not change it. So, it is still out. So, I am changing from 3, 4, 5 to 2, 4, 5.
So non-basic also can come inside.
So, I want to increase this objective function z, and what I see is that if I make x 1 or x 2 positive, then I might be able to do that, right. So, then if I have to do that, I have to make it basic. This x 1 x 2 were initially non-basic, but they have positive coefficients in the objective function. So, the idea is to try to bring one thing which was originally non-basic into the basic, and so you have to remove something, right, because it has to be a basis.
Yes.
So what you do is you look at, you choose one of the variables which you want to increase. So if you have a positive coefficient in the objective function, then each of these things, x3 greater than or equal to 0, x4 greater than or equal to 0, x5, each of these constraints tells you how much you can increase x2. In this case, the first constraint says that x2 can be increased up to 1. The second constraint doesn't say anything, you can increase x2 how much ever you like. The third one says you can increase x2 up to 2. But all these constraints have to be satisfied. Now, so I will increase only x2 up to 1. But then what happens is x3 becomes 0. Hence, I would say x3 leaves, x2 enters. The guy that became 0 can go, right? Anyway, those will be said to be 0. And the guy that enters is the one I have increased. Now it has to become non-zero. So in my new feasible solution, x3 will be 0 and x2 will be 1. So now what we should do is we should write x2 in terms of x1, x3 and x1 and x3. So this will become 1 plus x1 minus x3. This will just still be 3 minus x1. Here this x2 I have to substitute by this using this equation. So I have to say 2 minus x2, but x2 is 1 plus x1 minus x3. So if I work that in, I will get 2 minus 1. So I will get 1 here. One minus x1 plus x3, and let me also rewrite the objective function. So z, now I don't have, it's always written in terms of the non-basic variables. So now let's again substitute. So this x2 will become 1 plus x1 minus x3. So it will become 1 plus 2x1 minus x3.
Is this possible because the original matrix what we have is also having 2, 4, 5 as the basics?
No, you choose the basic.
Yeah,
We want the best basic.
Yes, sir. So if 2, 4, 5 is not the basic in the original matrix, then we can't do this.
Correct. But it will always be, because in this equation, this caused the, so yeah, it will turn out that it will always be basic if you do this pivoting method.
Right. So is there any confirmation?
Yeah, so that's because this increasing x2 sort of put this x3 at a constraint, which means that x3 actually depends on x2. So
So you can remove.
so you can now solve for x2 in terms of x3,
Yes.
which is exactly what we did. So now you can express, so it's just substitution. So now since we can write x2 in terms of x3, x4 originally we had written in terms of x1 and x2, but x2 can be written in terms of x3. So now I can just substitute it. So in fact, when we write down this tableau, this is exactly proving that these form a basis, because unless these form a basis, you won't be able to solve for these variables in terms of the other variables. So that's the thing. So somehow this pivoting already tells you that the new thing you get, it's forced to be a basis. Okay, so this thing is called a pivot step.
But so what's the confirmation that it does increase the objective function in every time?
This is the confirmation.
But we also subtract x3, so
But we are setting x3 to be 0, doesn't matter, right. So we increased x2 to 1. We have increased the objective function by that.
So initially there was x1 plus x2. Now we
Yeah.
have thrown off x2.
Yeah, but now we are going to set x1 equal to 0, x3 equal to 0. So now our new basic feasible solution is x1 equal to 0, x2 equal to 1, x3 equal to 0, x4 equal to 3, x5 equal to 1. This is our basic feasible solution.
So compared to initially it was.
So now your objective function has become 1, it has improved.
Initially it was 0, so now it is.
Now it has improved. And
One.
it is not an accident that it has improved. It has improved because we increased one of these variables. We didn't touch the others, so it's not like the other variables can decrease or anything, right? So we are always expressing the objective function also in terms of the non-basic variables. In this case, the objective function was already in terms of non-basic. Suppose there was an x3 here, but we have a formula x3 is 1 plus x1 minus x2, so we can remove it from the objective function also. So everything is going to be expressed only in terms of the non-basic variables. Yeah.
So now if we want to increase x1 and we go back to do the thing, we have to substitute x2 is equal to 1 and then continue.
Correct. So now there is no point in increasing x3, we should try to increase x1. Okay, but let's stop now and maybe you can think about how to do the next couple of steps. And the beauty of this is that you don't have to prove that the new thing is basic and all, it's all evident from the new tableau that you get. And you also keep track of the basic solution by looking at this column here, you keep track of the objective function by looking at this entry here. So, the tableau says it all, right, and you forget about everything else and just focus on these tableaus, and that is the essence of the simplex method. So, tomorrow we will just finish this quickly and then I will talk about some more interesting things that come out of this simplex method.